Okay, so in this one, we're going to discuss three main things. The CDF, which we already introduced in the previous lecture. We're going to give more of its details, discuss its inverse and why is it used, and so on. We're going to also introduce the empirical distribution function, define it, and say what it's used for. We're also going to introduce you to the world of resampling techniques by starting off with a main motivation. So without further ado, let's get started with some CDF properties. So as we discussed in the previous lecture, the CDF of a random variable x is defined as f of x, which is the probability that x is strictly less than or equal to x is less than or equal to x, right? So that was the main definition. Now, from this, we mentioned two direct consequences in the previous lecture, which are that, the function, the CDF function, is bounded between 0 and 1, right? Well, that's one of its main properties, and more formally, we capture this essence in the following limits. So the limit as x goes to minus infinity of f of x is 0. You could see right here, the more we're going to minus infinity, this is going to 0 or is already 0, right? Also, the limit as x goes to plus infinity of f of x, right, it is 1. So it's bounded between 0 and 1. This is not sufficient to say my function remains between 0 and 1, right? Because anywhere in between it could pop over. So to complete this, bounding, you have to come and tell me that f of x is a non-decreasing function. Either it remains constant or it's increasing, right? That we say f of x is monotone in the sense that fx is less than or equal to fy given that x is less than or equal to y, right? So combining all those three, we can say that f of x reports a probability, which it does right here from the definition, and hence f of x is bounded between 0 and 1. We can also say, due to this accumulative property of the CDF, we can come and say the probability that x takes on a certain value, x, right? It is nothing other than f of x minus fx minus, where x superscript minus stands for a limit of x plus epsilon, where epsilon is negative. Well, it's better to write it that way. So x minus epsilon, where epsilon is positive and it's going to 0. So what do we mean by this? Let's say you're interested in directly interpreting a certain probability from the CDF. That works for discrete cases. Okay, so let's say I have the following distribution. So x takes on a value, let's say 0 and 1. Let's say we have a Bernoulli distribution, right? So it takes on value 1 with probability p, value 0 with probability 1 minus p. How would the CDF look like? Well, using this definition, we can say that f of x will look something like this. So it's 0 everywhere before 0. At 0, it will jump to a value of 1 minus p, right? It will hold at 1 minus p, and at value 1, it will jump to 1, right? Because we added before plus p to the 1 minus p. So it will jump to 1 and continue like this, right? This is how a CDF of Bernoulli would look like. And what this property 5, is telling us is that if you're interested in, computing the probability that x is, let's say, 0, right? So we come here at 0, f of 0 is 1 minus p, and f of 0 minus would be, in that case, anything behind 1 minus p, right? Anything behind 0, the amplitude of f behind x equal to 0. So it's 0. Combining those two and using property 5, you get that the probability that x is equal to 0 is 1 minus p minus 0, which is 1 minus p. The same thing works for 1. You get 1 minus p, which becomes a p. Now, if you're anywhere other than 0 and 1, You're going to, let's say, grab this point which never occurs. This value, let's say 0.7, never occurs. So f of 0.7 is 1 minus b, and f of 0.7 minus is also 1 minus b. So if you go back just a bit, it's 1 minus b. So subtracting those two, you get that the probability of 0.7 is 1 minus b minus 1 minus b, which is 0, right? And this works for any point other than 0 and 1, right? So one last thing maybe we didn't mention is the right continuity of the CDF, okay? So what does that mean? It means that the limit as x goes to y plus of f of x is nothing other than f of y, where y plus is also a limit as epsilon goes to 0, where epsilon is positive, of y plus epsilon. Okay, so that's just telling you that your function is right continuous. It's not left continuous, because if I come and stand at a point, right, let's say the point 0, at 0 minus, you jump down to 0. But at 0 plus, you still reserve the value of 1 minus b, okay? Right, so that's about it. Let's compute some CDFs using property 7. So if you have a certain PDF, if x has a certain PDF, p of x, we said in the previous lecture that a PDF is the derivative of a CDF. Well, how do you compute a CDF from a PDF? Using this, you simply get that f of x is the integration of your PDF, right? That's what you get. Now let's compute the CDF of, let's say, I have a uniform distribution, right? And this is only defined for the continuous case. So let's say x is a uniform distribution in 0, 1, right? And I'm interested in the CDF, and I know the PDF, which is 1. It's 1 over b minus a, but in that case it's 1, only when x is between 0 and 1. This is an indicator function. Okay, so using the definition right here, f of x is then computed as follows. So it's the integration of one indicator function, where this time u, because it's p of u, so replace x by u to avoid confusion, because here we have on the upper integration limit x. So that's why we denote here as u. So this guy is 1 only when u is between 0 and 1, so the integration is between 0 and x, right, of 1 du. So what you get here is x. And this is, it's only x only when x is less than 1, and of course greater than 0. If x is greater than 1, then this integration splits as follows. So it's minus infinity till 1 then of 1, right? Plus 1 till x of 0, because your u exceeded 1, so you get a 0. So this integration goes away, and here we have a 0 because I is 0 when u is less than 0, and hence you get a 1. So this works only when x is greater than 1. So if we want to plot f of x, in this case it will look something like this. So before 0, it's a 0. After 1, it's a 1. And in between you have x. So this guy is y is equal to x. This is y is equal to 1. And here, y is equal to 0. Okay, let's give another example. Say x is an exponential distribution with parameter lambda. This means that the PDF is lambda e minus lambda x only when x is positive and 0 otherwise. And also represent this using the integrator function. Now let's integrate to get the CDF minus infinity till x of lambda e minus lambda u du. You do the integration, and be careful here, it's 0 from minus infinity till 0, and we're assuming x here is always positive, so this minus infinity is 0 right now till x. This is a simple integration, you can easily do it, and you will get So it's 1e minus lambda x, only when x is positive. Now to see how this looks something like this. So an e minus lambda x looks something like this. Then flip it. Be careful, this is 1 right here, or minus 1 because this is 1. And this is an e minus lambda x, and then push it up by 1. So it will look something like, in the end, it would look something like this. If we push the dotted curve by 1, it would look like this. Okay, so this is your CDF of the exponential function. Let's do this on R. So let's define an x-axis which goes from, let's say, 0 till 5 or till 10 with steps of 01, and your y is the CDF, call it f, which was 1 minus lambda or L times x. Let's call a lambda of 1, right? And now let's simply plot. And there you have it. So I'm going to plot single line, and there you go. This is your PDF, like this. Let's put a red color. There you go. Okay? Okay, now let's talk a bit about statistics and resampling. So let's say you're in a situation where you're given n random samples. Okay? Not necessarily IID, you have n random samples. So as we said in the previous lecture, a statistics, denoted as S subscript n, and the subscript n is telling you the sample size. It is nothing other than a function of your samples. So any function you create out of your samples is called a statistics. Okay? Examples of statistics are the following. You have the sample mean, such as you just do a simple average of your samples. You've got the sample max. So the function here would be the max of your samples. So you've got the sample min, the minimum of your samples. We've got the sample range, which is given a certain sample, right? Let's say x1 is here, x2 is here, x3 is here, x5 is here, and x4 is somewhere here. So the range would be x4 minus x1. What did we do? It's the max minus the min. So the max in this case is x4, the min is x1. We've also got the sample variance, which is defined as 1 over, not n, it's n minus 1. This is because I think we're going to see it in later lectures. This is for, let me just continue the definition first of all. So the sum of xi minus x bar square, where x bar is the sample mean. So it turns out that this guy is unbiased. Okay, so if you put an n, then you're going to have a certain bias, something like that. We're going to see it later on. Okay, some other ones that you might not encounter pretty often are, let's say, the number of observations above t, a certain level t. So in that case, your S would look like this. It's the sum of indicator functions, so you're counting some events where xi exceeds t. So let's say your t is 2, and you've got, I don't know, x1 is 0, x2 is 1, x3 is minus 1, x4 is, let's say, 5, x5 is pi. Let's say that's what you observed. So how many of them are greater than 2 or equal to 2? You've got 5 and the pi, so 2. This function will evaluate at 2. If t is 2, it will evaluate to 2. You've also got the rank of your first observation, which is x1. And what does that mean? It's a function, a statistic, which is defined as 1 plus the sum of all other indicator functions of the events where xi is greater than x1. So it's as if we're doing the first function, but for x1 And instead of, comparing x1 with x1 because it doesn't really make sense, we indicate that x1 is okay. So in this function right here, if we have this sample right here, and we would evaluate this function, it will return 1 plus the number of samples that are greater than the first observation, which is 0. In that case, you have x2, x4, x5, which are greater than 0, hence 3 samples. So 3 plus 1, it would return 4 for this particular sample. For another sample, I don't know. You have to observe the sample and do the same thing. Now, extreme cases right here would be if x1 is the largest number of the samples, right? You would get 1 plus 0, which is 1. Because there's no other sample greater than x1 if x1 is the largest. So 1. And if x1 is the smallest, you will get n. Because you have a 1 plus, and if x1 is the smallest, then all xi's are greater than x1, hence you get n minus 2 plus 1, which is n minus 1, plus 1, which is n. Okay? You've also got the second moment sample, which is defined as a sample average of xi squared. You've got third moment, you put xi cube, nth moment, or kth moment. You can replace this square by a power k, right? It's not kth second, it's not second moment anymore, so it's a kth moment. Okay, so this is it for some popular or mostly used, I would say, statistics. There's of course other ones that are really popular, but I've named a few of the known ones. Now to, if we have that x1 down till xn are generated from not necessarily the same sampling distribution. So let's say x1 is generated from f1, x2 is generated from f2, down till xn being generated from fn. So what do we have here? The distribution of these n random samples is completely determined by their joint CDF. So f, x1 denoted as follows. So it's an n-dimensional function, right? In the case of IID random variables, so when they're independent and identical, then you have that f1 and fn are all the same, call them f. And since they're independent, then the joint CDF becomes a product of each of the CDFs. And since each of the CDFs are the same, then you simply get f power n of x. This will be your joint CDF. And also this works for the PDF. So you could also say that the joint PDF, in the case of IID samples, is the product of each of their independent PDFs. Now, let's say we have a certain statistic. The statistic is indeed, as we mentioned in the previous lecture, this quantity would be random. Because the input points, x1 till xn, are random. So it is natural that a function of random samples would be also random. So with that being said, then let's say you want to study your statistic, what would you do? You would indeed take a look at its CDF or PDF. That's a natural thing to do. And since Sn is a function of x1 down till xn, then this CDF would be completely determined, right, by the joint CDF. Because to derive the CDF of Sn, given the joint CDFs of x1 down till xn, then it's just a matter of a simple calculation, right? You have the joint CDF of your x's, then any function of this joint CDF could determine, so if they're IID, then instead of all this, you would have an x power n of x, right? So recapping everything right here, so the main problem that we have is that given samples x1 down to xn, right, that are drawn from a distribution f, where f could be a vector, right? F is f1 down to fn, meaning that x1 is drawn from f1, xn is drawn from fn. It's just a shorthand notation for all this, okay? So given this, i.e. given f of x and their size n, you will want to determine the joint CDF, and then from that you would want to determine the CDF of your statistic. So if we take a look at this right here, so given f and n, get fsn, right? So we can see this as a mapping. So say my mapping is psi, which goes from, we have a couple here. So fx is coming from a certain, collection of all possible CDFs, right? And the second entry of this couple would be a natural number, but the sample size couldn't be other than that. And you would return another CDF. So in other words, my psi takes in f and n and would return an fsn. So as an example, let's say that my x1 down to xn come from a standard normal distribution. And let's define a statistic, which is the sample mean or sample average. Then the question is here, given f, given n, f is the standard normal and n is n, get fsn. So how do we get the CDF of the sample mean? Well, all I have to do is using the definition, so fsn, you could do it like this. It is the probability that the Sn is lower than x, right? Which is the probability that 1 over n, sum of xi's, is less than x. Which is also the probability that sum of normal distributions is less than n, x. Well, this step is unnecessary. You can just go here and say that this guy, in case of IID, random variables, right, they're identical. But let's say they're also independent, then a sum of standard normals is again standard, is again zero mean, is centered. But this time with variance would be 1 over n. As simple as that. And why is that? Well, if you take a look at the expectation of 1 over n, sum of xi, you'd get 1 over n, sum of the expectation, which is 0, because of here, or because of here, and the variance of 1 over n, sum of xi, a constant will be extracted as a square, sum of the variances of xi in case they're independent. This here assumes independence. And the variance is 1, so you'll get a sum of 1's n times, so you get an n over n squared, which is 1 over n. This explains the 1 over n here. So in that case, your Sn would follow a normal distribution with 0 mean, variance 1 over n. Now, what is the CDF? The CDF of a normal distribution is, so if n is mu sigma square, if that's the generic normal distribution, then its CDF would be half into 1 plus the error function of x minus mu over sigma root 2. So you'd have to, work out the integration of the PDF, which is a bit, fuzzy, but it's okay. You'd get this. So anyways, recapping what we did here. So in my case, if the variables were assumed to be IID, then my f is just 1f. It's not a vector, it's 1, because they're all the same. So it suffices to give me only one CDF and not a collection. So I have that this fx is the CDF of a normal distribution. Let's call it phi of x. So this guy is a phi of x. And we got that fsn is phi of x, but with variance 1 over n. So phi of x here with variance 1, we get a phi over x with variance 1 over n. Now, if we change n to be n plus 1, then you're going to get a 1 over n plus 1, right? And therefore, you can see that the sample size, if you change it, then the CDF of your statistic will also change, right? So that's 1, going back to n. If you also change the CDF of your samples, the CDF of the statistic will also change naturally. We're just seeing how this mapping works. So let's say I no longer have an n01 right here. I have an n13. So mean 1, variance 3. So this variance here is 3, no longer 1, and the mean is 1. What would FSN look like? It would not look like 0, 1 over n anymore. It's no longer a normal 0, 1 over n. No, it would be an n 1, 3 over n instead. So this 1 over n would be a 3 over n, and it would be of mean 1, right? So I'll just erase right here, erase right here. Go back to what we have. So any modification of the CDF of the random samples or / and any modification of the sample size will indeed affect the CDF of the statistic. This is how we see it through an example. So what do we conclude right here? So given f and n, the distribution of any statistic of the samples, right, is determined or fully determined by f and n, or by x1 down to xn. Those are the same. Okay? Now, even if we cannot write down the function of fsn because it might turn out to be complicated, as long as we can sample from f, we can generate many sets of size n that are random, and therefore this will allow us to compute Sn, the statistics of the random samples, and find out the distribution of Fsn. You get what I'm saying? So if you cannot explicitly write down the CDF of Sn, what you're doing could be equivalent, which means that if you're generating samples of size n or n samples, you could just compute Fsn for every bunch of n samples, and this will allow you to generate Fsn. You get what I'm saying? So let's say in the more generic case I have n equal to 2, x1 is a standard normal, and x2 is a Cauchy with parameters 2 and 3, right? The CDF right here will turn out to be hard to write down. So what do? You don't stand there and just look at those two samples. No, you could simply, if you're given Sn of x1, x2, you just compute it by observing samples, right? And hence, this is the equivalent of generating from Fsn, okay? But what are you doing? Instead, you're not generating using Fsn directly, you're generating using x1 and x2, or even more, f1 and f2, right? So here you can see that the CDF f is really important in analyzing the distribution of any statistic. But in practice, as we said, the CDF is unknown, so there's nothing you can do. You can't come down and write it analytically. So you can't come and do as we did here, like do the math and tell me, oh, so the CDF of my statistic is n 0, 1 over n. It doesn't make sense in practice because you're just given x1 till xn. You're just observing them. No one is telling you, oh, they're coming from a normal distribution. No. So what do? You compute the statistic and you're generating samples from Fsn instead. So the main question here, so what do? So the main question here is, given x1 down to xn, how do we get f? Namely, how to get their CDFs. So one way to accomplish this task or to answer this question is to estimate the empirical distribution function. We'll answer this question just after we take a look at some CDFs on R. So let's practice a bit how to use R to plot some CDFs. Okay? So let's say I want to, plot the CDFs of EXP1, EXP2, EXP5, and EXP10, right? How do I do so? Well, before we start plotting any CDF, we saw in the previous lecture how to generate random numbers using the R, for example, norm. So R stands for random, and D would stand for distribution. Well, we have something similar, which is P. So P norm would return CDF, would evaluate the CDF at a certain X value. And we will use the P to generate CDFs of distribution. So for example, if I want to plot the exponential distribution, all I have to do is plot P exponential, and I'll just assign it some values. So let's say sequence 0 to 5 with steps of 01, and I need to specify my rate or lambda. Let's say my lambda is 1, run. So let's say minus 5 till 5, and this is how the CDF of the exponential looks like. Now let's be more neat. Let's do stuff like they should be done. So let's define my x-axis, right? Let's say I want to see everything from 0 to 4 with steps of 0.1, right? Now, okay, let's plot first of all. So on the x, I'll assign x values. On my y, I would evaluate the P exponential at the x-axis with rate 1, okay? I want a line and I don't want those circles. A line width of, let's say, 2 is okay, and my color, let's set it to Dodger blue. Let's see what we have. This is what we have right now. Good. Now, let's say I want to plot on the same plot another CDF. Okay, I want to compare, I want to see how the CDF behaves with different rates, with different lambdas. i.e., I want to see now exponential 2, how it looks like. So all I have to do, and I shouldn't do this mistake, so if I do a plot and I just change this to, and I say, oh, I want now a sky blue color, I will get 2 plots. That's not what I really need. I want them to overlap on the same figure. So instead of plot, I'm going to use lines, right? So lines will plot it on the same figure. Now, let's do the same thing for exponential 5 and exponential 10. So I'll change the rate right here, and I'll change the color. So midnight blue and, I don't know, a blue, okay? So run, and there you have it. Now, it's really hard to see which is which. So it's best to place a legend, right? So a legend is going to tell me, oh, this plot belongs or it corresponds to this rate or lambda, right? So how do I do that? Well, you first have to set the position. So let's say I want it on the bottom right. So bottom right. And now the legend, which is a vector specifying for each plot its corresponding description. So it's done by order, so Dodger blue, sky blue. So it's done by order, rate 1, 2, 5, and 10. So right here I'll put exponential 1, exponential 2, 5, and 10. Let's take a look, and there you have it. Now also it's hard to, read this because it's not telling me anything. It's not telling me this color is for this plot, so I have to come here and specify the color. So the colors are going to be in the same order I plot. So the first one is Dodger blue, the second one is sky blue, so I'll just copy paste them here. Dodger blue, sky blue, midnight blue, and last but not least, okay, run, still not telling me anything. I think I have to specify a certain line width, and there you go. Okay, so the same line width as the plots right here. So I could have said line width 5, but it would appear more thick. It's best to say or to mention the same line width as plots you have. Alright, okay, now we have a better feel of what's going on. So you can also come here and specify the main, the title. So we can say CDFs of exponential distribution with different rates. Okay, you can change the x-axis, x label to x, and the y label to something like probability that my x is less than or equal to x, which is my f of x, right? Okay, good. Now let's generate or update my notebook as such. Looks good. Now let's plot CDFs of different distributions. So let's visualize the CDF of a uniform distribution from -4 till 4 and the normal distribution of the standard normal distribution, and as well the exponential distribution of parameter, let's say, I don't know, 3. Let's do this quickly. So first of all I have to do is specify an x-axis. I'll go ahead and say I want from -5 till 5 with steps of 0.1. That will do. And if it doesn't, all you have to do is just change it. So over here I could have say I want to visualize from -4 till 4. I run, and there I have it. Okay, it's just like tweaking values. So let's say you're interested from 2 till 4. You get this. It's not sufficient. You need to expand it more and more. There you have it. Okay, so going down here, I'll start with -5 till 5, right? And so let's plot first of all. The x is my x-axis and the y is, so first of all I want the uniform distribution, so it's p uniform. Parameters would be the min and max, so 0 and 1, right? Or -4 and 4, right? And the max is 4, and just pass it my x-axis as such. So run. There you have it. As you can see, this is what we derived in the course. It was f of x is equal to x. So a straight line. So I'm not satisfied with the line width. Let me set it to 2 or to 1. And the type, I think that's the problem. So the type, okay, looks good. So line width, set it to 3, 2, there you go. Okay, so this is how you do the uniform distribution. Do we have other parameters we can play with? Say I want the color, or it looks nice. Now let's copy paste this guy, put it here, lines. Now let's plot the normal distribution. So x is x-axis, y is p norm. So I want to evaluate that x-axis, right? So in case I don't pass it any parameters, means it's the standard normal. The SD and the mean are respectively 1 and 0. So if I do this, it's the same thing. So line width to be 2, type is an L, and this time a color is, let's say, sky blue. There you have it. I'll just copy paste this, and I'll change this p norm to a p exponential because I want to plot the exponential 3. Be careful, you don't want this. Instead, you want to specify the rate to be 3, right? And the color, let's set something like lime green. Perfect. What's missing is a legend, right? So a legend, I want it to be on the bottom right. I have an error. It's missing values. Okay, so a legend. See, the first one was a uniform from -4 to 4. The second one was the normal 0, 1. And the third one was an exponential 3, right? Bottom left, bottom right. You can put it on a bottom left if you want. You can top right, which is not good because it's overlapping here. I'll just go with top left. Let's check if there's a center. There is, but top left would do. Now let's specify the colors. So a vector specifying the colors. This one was sky blue and line, and a line width of 2, right? There you have it. In case you want to specify a title, go back here for main, comparing CDFs of the following: too big, an x label of x, and a y label of, f of x, right? So in case you want to limit your y, to view between two values, all you have to do is go here, y limit, and specify a vector of min and max. So between 0 and 1, that's what I'm doing. Between 0 and 2 would return this. Between 0 and 5, you get what I'm saying? So return it back to 0, 1. You also have the x limit, which does the same thing, but for the x-axis. So let's say minus 10 till 10. It's already between minus 5 and 5. That's like a window on the x and y axis. Now, let's see how the normal CDF behaves with different variances, i.e. sigma square. Okay, I'll insert an R code. I'll generate a new notebook. I'll update my notebook. Okay, so that's the goal right here. Again, the x-axis. Let's see. I'll go again with minus 5, 5 with steps of 0, 1. Okay, so first I'll plot x-axis, then y, which is a p-norm evaluated at x-axis, right? And first I'll see a standard deviation of 1. Okay, or let's start with 0.1. Line width, let's set it to 3. Type is a line, and the color is blue. Run. This is what you get. Now I'm going to copy this exactly 4 more times or 3 more times and update those to be lines, right? Copy paste this 4 times and change here the values. So 1, I would like to see 2, maybe 3, and 5. Update the colors. So let's say I want the Dodger blue, sky blue. What else do we have? Orange maybe, and okay. Let's run to make sure. There you have it. Now let's insert a legend on either the bottom right or top left. I'll go with bottom right. And here let's insert description saying SD is 01, SD is 1, it's 2, now it's 3, and here it's 5. Run to make sure. Okay, let's insert colors. So blue, Dodger blue, sky blue, orange, and magenta. Good. And a line width of 3. There you have it. Let's put a better description. So main is CDFs of normal distribution with different sigmas. Okay, so yeah, that's about it. In case you want to change your x label to x and y label to f of x. Perfect. Okay, let's do one more thing. So let's do the same thing here. I'll copy paste this description, but now let's see how it behaves with different means. Update my notebook. That's a pretty notebook. Anyways, I'll just do this. I'm going to copy paste all this code right here and do some minor modifications, because really all I have to do is fix my standard deviation, let's say to 1, okay, and see how this goes with different means. So let's say mean 0, mean 1, 3, and a 4. So I've got normal distributions. I'm visualizing their CDFs where those normal distributions have the same variance but different means. So here I'll change the description of the legend to be mean 0 down to mean 4, and here the title to be with different means. And there you have it. You can see here that we're not visualizing what's going on here, so we'll go back here and change the upper limit maybe to something like 8. There you have it. You could see that for mean 0, the CDF is centered at 0. Mean 1, the CDF is centered at 1, 2, 3, and 4. Now, another useful thing to do is maybe let's see how the CDF of a t-distribution looks like compared to that of a normal. So we'll go here, insert R, let's define an x-axis from minus 4 to 4 with steps of 01. Let's plot x-axis, p-norm. I want the standard one, so I'm just going to pass it the x-axis, a line type, line width of 3, and color, let's say lime green. Run. This is the normal. Now on top of that, I want to observe the t-distribution, so pt, x-axis, and what does it take? There's the degrees of freedom of a t-distribution. So I'll pass it maybe 1, give a line width of 3, and let us set the type to L maybe, and the color. Now let's see how the t-distribution behaves with different degrees of freedom. So 2 right now, color green. Let's change it because we have a green already. It's a blue. Okay. Now let's plot 1 with degrees of freedom 5, but color red. It's approaching more and more the normal distribution, right? And let's say a high degrees of freedom of something like 50. And color it sea green. And it's really on, or let's color it black. You could see it on the normal distribution. So in case you don't see it, let's insert some legends on the bottom right. So the first thing I have is an N01, a standard normal, then T distribution with degrees of freedom equal to 1. Okay, good. I'll copy paste this. I'll change the degrees of freedom. Not bad. And now let's specify the color and the line width that was used. Okay, so you can see that the black and the green are overlapping. So in case you want to take a better look, you can hit this button right here. It will generate this figure for you. Okay, you can see that the black and the green are coinciding. If you want to zoom in to have a better view, let's go back here, set the x limit 0 till 2, and let's set the y limit between 0.4 and 1. You could see that the black and the green lines are coinciding, and each time we increase the df, the degrees of freedom, you're seeing it approaching the normal distribution. This is actually a property of the t distribution. It tells you that you can approximate your t distribution as a normal distribution for a large degrees of freedom. Right, so we saw how to, plot different CDFs using R. So now let's continue the answer of this question, or one possible answer of this question. So given random samples, how do we estimate F, or how do we get F? So one answer is using the empirical distribution functions. So that's another function, and indeed it's a statistic because it will turn out to be a function of the random samples, x1 through xn. It's not any statistic, it's one that estimates the density or the CDF distribution. So if we take a closer look at the definition of the CDF, which is defined as the probability that x takes on a value less than or equal to x, right? So let's fix x at a point x0 and take a look at this point estimate, if you will. So that's one point of the complete function. How do you estimate fx0? That's the question. So using the definition, we can see that it's a probability. So it's nothing other than a probability. And hence one natural estimator is, you take a look at the proportion of success of this event. Namely, you can estimate, hat means an estimate, fx0 as the total number of samples that are less than x0 over the total number of samples. So in other words, to have a more concrete definition, it is the sum of all events that are less than x0 over the total number of samples. So we can write it as such as well. So this is for one point x0. You can go ahead and generalize this to all points. So you're estimating a function right now. Instead of x0, you have an x. So this is what we call the empirical distribution function, because you're really estimating the distribution function through empirical observations. So through the data you have, you're estimating the CDF. Now, if you want to see a small example on R, examples of EDF, okay? So I'll insert some R code. Okay, so let's say my data X, so X1 down to Xn, are drawn from a uniform distribution. So I'm going to pick n is equal to 100. So I'm observing 100 random samples drawn from the standard normal distribution, okay? If we take a look at, the true CDF, so I'll define an x-axis, which, as we did previously, let's say from -5 till 5, discretized with 0.1 steps. So x-axis and a p-norm of x-axis, right? So a line And there you have it. This is the true one. So I'll color it with, let's say, sky blue. And I'll increase my white line width till 5. Okay? This is the true CDF. Now let's try to estimate this CDF using the EDF. So R has a function dedicated for that. Instead of you having to go ahead and do a for loop and estimate it for each point, you know, evaluate this test statistic at each point, you can go ahead and actually use the eCDF function. You only have to pass it your data x and plot. So there's a warning. So indeed, I shouldn't pass it this. So there you go. There you have it. It's close to the CDF. Now it looks ugly. Let's do something nice. So we can actually call there's a property here called do points, I think. Set it to false. So you get this line right here. It's smoother to look at. Indeed, because the eCDF is evaluated at points, so there you go. If you have less points, it will look more rough because it's discrete. It's always discrete. Depends on the sample size. So 20, there you go. 30, you have this. Let's plot this for different ends, right? So I'm going to copy paste this right here because we don't need it on top. I'll do this. Copy this here, right? There you have it. Let's change the line width first of all because it's too thin, right? And let's set the verticals. Looks much better like this. I like it. I like it. And now let's plot multiple lines. So for different ends. So let's say for n in, I don't know, sequence, then let's say I want 100 with steps of 10. Let me remove this n and copy paste those here. Let's insert parentheses. There you have it. I know it's not the best. Let's do step sizes of 20. Okay, 30 maybe. The higher n is, a better estimate you get for the CDF using the eCDF statistic. Now, if all of them have the same, you know, size, so let's set n to 100 and let's plot it multiple times. You have to know that eCDF is a random quantity. It's not fixed. So if I come and generate it again, you're not going to get the same EDF. So right here, n would be something like, I'm not going to call it n, I'll call it k, and I'll do it, let's say, 10 times. So run. Now that's what I mean. Here you have the same n, the same distribution, right? But each time you're generating a different realization of your eCDF. So the quality of estimates are roughly the same because you have the same f and the same n, right? So you're going to get the same FSN. Going back here to the course to be consistent, you have the same f and the same n, but you're getting different FSNs. It's not that you're getting, oh, no, you have the same FSN, but you're generating different realizations from the same CDF, FSN, right? In this case, SN is the EDF. Let's increase n now to 1,000. You will see them that they're closer and closer to the true CDF. Now it's 10,000. As you can see, they lie on the CDF. If you want, we can zoom in. So let's plot with x limit to be 0 till 2. Even here you can't see. So let's put 1.8, 1.9. You have to go on a really deeper level because you're getting actually good estimates. So that's one instance of the EDF. Right, so now let's let's look into the EDF more closely, i.e. we're going to, get its mean and its variance to see the properties, if it's biased, unbiased, how good of a variance we have, and stuff like that. So as we said right here, it is nothing other than the sum of indicator functions. So let's take a look at this indicator function more clearly. So If we look at I, if xi less than x, it outputs 0 and 1. So it's a 0 if xi is greater than x, and 1 if xi is less than or equal to x. So this is a random variable, right? Because it is a function of another random variable, xi, right? And this random variable is just giving us 0 and 1. So this ixi follows a Bernoulli distribution with parameter p, right? And what is p? It is the probability that, if I call this guy right here yi, it is the probability that yi is 1, right? So it is the probability, that xi is less than or equal to x. In other words, p is nothing other than the CDF of xi, right? So this might sound a bit weird, but the rate, which is a probability, is a CDF. That's amazing. That's really amazing. Take a look at this. So it's as if you have a coin tossing experiment, and the probability of you getting heads is a CDF. Okay? So in that case, we say that yi, which is ixi less than x, is a Bernoulli distribution with rate f of x, the CDF of x. Okay? Now we can compute the expectation of yi, which is 0 times probability that yi is 0 plus 1 times probability that yi is 1. So it is p, which is f of x. In the same way, the variance of yi is, you can use the definition, you can make use of the fact that we derived it maybe in the previous lecture, the variance of a Bernoulli distribution, right? Go back here. So that's the expectation p. You can go ahead here and say, oh, I have the variance of x is the expectation of x minus p squared, because p is the expectation of x. So you'll get a sum of x multiplied by x minus p square multiplied by p of x, where x is in 0, 1, right? So you'll get a p squared times p of 0 plus 1 minus p squared times p of 1, which is, let's remember that p of 0 is 1 minus p, so p squared into 1 minus p plus 1 minus p squared into p1, which is p. So let's factor common terms. We've got a p and a 1 minus p in both terms, so p into 1 minus p. What remains from the first term is a p, and from the second term is a 1 minus p. So in total, you get a variance of p into 1 minus p. Going back here, this means that the variance of the Bernoulli distribution I have is simply p into 1 minus p, which is f of x into 1 minus f of x, right? Now going back to the more important function that we're studying f hat of x. So f hat of x, again, is written in terms of yi. It is nothing other than the sample mean of yi, right? So the expectation of f hat of x is 1 over n sum expectation of yi, which is 1 over n times f of x, which is f of x, hence unbiased estimator. And the variance of f hat of x is the variance of 1 over n sum of yi's. 1 over n goes outside as a 1 over n square, and since each yi is independent, we have iid, so the sum of variances of yi, which is 1 over n squared, times variance of yi is independent of I, right? Because they're IID, they're identical. So n times fx into 1 minus fx. This cancels with this, and you will get f of x into 1 minus f of x over n. Good. So we conclude that the expectation of the EDF is the CDF, and the variance of the EDF is this function right here. So it's the CDF times the survival function, if you will, or the complement of the CDF divided by n. What does this tell us about f hat x or the EDF? First, we see that it is unbiased, and second, we see that as n goes to infinity, this quantity right here is surely going to 0, because we know that f of x is bounded between 0 and 1, and so as the CCDF as well, bounded between 0 and 1, and hence as n goes to infinity, this quantity will go to 0. So this means that f hat of x is a consistent estimator of f of x, right? We conclude that f hat of x will converge to f of x by probability, not by distribution, because a consistent estimator converges in probability, okay? Even though we have two distributions, this convergence is in probability. Now, in addition to this, the EDF also has the following important feature. Using, the CLT, you can use the CLT. You could say that f hat n of x minus the mean multiplied by the square root of the sample size converges in distribution to a normal of 0 mean and variance sigma square. So f of x 1 minus f of x, right? So in the asymptotic regime, fn hat, the EDF, behaves as a normal distribution. Right, so let's see what we mean by this more clearly on RStudio. So I've written it here, and this is what we want to visualize. So there's this quantity on the left. Actually, go to the quantity on the right. That's our main question. So to do this, we're going to generate multiple times. So for k in, let's say, 1 till n, where n is our sample size, because we're doing this pointwise. I'm going to do it only for one point x. Let's say x is 0. So let's first specify n to be 1000 and my x to be 0. So the true value, which is f of x 0, is the p norm at 0, right? Because it is f of 0. This is f of 0, i.e. this guy right here, okay? At point 0. Okay, so each time we're going to generate f hat n. How do we do that? Well, first off, we generate normal values. Let's say each time we'll generate 1000. We need the function fn hat of x, which is ECDF of x. Now we need f hat n at x0, which is e at point 0. So fx0 hat is e at point 0. Okay? Now we need to save it in a vector every time so that we plot the histogram in the end, right? So fn, so fx0 hat vals is an empty vector, and each time I'm going to append this value, right? Now each time we're appending this value, we don't want this value, we want this value minus f0 multiplied by square root of n, so minus fx0 times the square root of n, right? Now let's plot a histogram to see what's going on. So fx0 vals. It looks like a normal distribution. Now to make sure, let's plot the normal distribution of that guy. So on top of that, I need lines, and we need x values. So we see that the values are somewhere between minus 1.5 and 1.5. So x-axis is sequence. Let's go on from -3 to 3 in case, and 0.1 distributions, steps. So the y in this case will be a d-norm because it's a density, PDF. Evaluated on x-axis. Is it centered? Yes, because here we have 0, so 0. And what is the standard deviation? This guy is the variance, so the standard deviation would be the square root of f0 or fx0 multiplied by 1 minus fx0, right? Let's run. You can't see it because the histogram is reporting frequencies, so to cast that to densities, all I have to do is set the probability field to true, meaning that I need a density. Okay, stuff are looking better. Let's color. Let's use this time a rosy brown. I like that color. Okay, you see that the y limit is cutting off some values of the true density. So I'm going to set my y limit between 0 and 1, and I'm going to set more breaks, more bins. Good, looks good. Now let's increase the value of n a bit to 2000. So it looks like it's a good fit. Okay, looks good. Let's return this to 1000. It looks good to me. So this is how we verify this convergence. So the black line is the normal distribution, the density, the PDF of a normal distribution. The rosy brown histogram is the empirical one. So we see convergence. And this is only at one point x. You should do this for multiple x's to verify. Okay, let's talk about resampling using the CDF. Okay, so what do we mean by that? Let's say you're in a situation where you have no access to any random generator other than the uniform generator, the uniform distribution, which is between 0 and 1. Let's say you don't have samples other than that of the uniform distribution, and from those samples you would like to generate other random samples that follow another distribution. So how do you do that? So let's say you would like to generate x1 down to xn coming from a CDF f of x. Okay? How do you do that? Using your u's that follow a uniform distribution. And you have those, but those you would like to get. How do you do that? Well, you can make use of the following property of the CDF, which tells you that assume you have the following random variable, which is the inverse of the CDF with u. Assume you have this random variable w. What is w? Well, if we take a closer look at the CDF of w, by definition, it is the probability that w is less than w. Now let's replace the representation of w, which is the inverse u, and u follows the uniform distribution. Now do the composition of f on both sides. Indeed, because f is a non-decreasing function, so the inequality is preserved, and now f and f minus 1 cancel out, you will get the probability of u less than or equal to f of w. And what is this? You can go ahead and say it is the integration from 0 till f of w of the PDF of u, right? Which is 1 dw, and you will get f of w. And what is that? It is the CDF of x. And there you have it. So if you want to generate random samples using the CDF f, you can do so with the random samples of a uniform distribution, simply by taking this random variable. So generating x is as easy as generating the following. Okay, so all you have to do is just compute the inverse of the CDF at the random uniform samples u to generate any other random sample following the CDF f. Okay, so that's one. Another property that we have is imagine x1 to xn come from CDF f of x. Now let's take a look at w, or let's call it something else. Let's call it v is f of x, this random variable. How does it behave? Well, let's take a look at f V of V, which is the probability that V is less than or equal to V, which is also the probability that f of x is less than V. Now let's do the inverse on both sides. X is less than or equal to f inverse of V, right? Now what is that guy right here? It is the CDF of f of x. So it is f of f minus 1 of V, which is simply V. And notice that V only takes values between 0 and 1, okay? Because it's a CDF. So we conclude that V is actually a uniform distribution on 0 and 1. So if we take a look at this, and X is generated from F, and if you take a look at the random variable f of x, it will be a uniform distribution. Now inversely, which we did here, if you take a look at y, where y comes from a uniform distribution, then x will have to be generated from f. Now let's see a quick example on that. Imagine I would like to generate x from the exponential distribution. The CDF, which was derived previously in this course, was of the following form: 1 minus e minus lambda x, right? So how do we write the inverse CDF? So we get e minus lambda x, which is 1 minus f of x, log on both sides. Therefore, x would be minus 1 over lambda log 1 minus f of x. So this is my f minus 1, right? So f minus 1 of u would be minus 1 over lambda log 1 minus u. Now, this means that to generate random exponential samples, all I have to do is generate uniform samples and compose them with this function so that they look exponential. Now let's do this on R. So I've got R in front of me and the problem is right here. So let's generate x, which has to follow an exponential distribution of rate 2, not using the R exponential. No, we don't want to do that, right? We want to instead generate such x's using this resampling method, using the inverse of the CDF by giving or feeding the inverse of the CDF uniform distributions in the interval 0 and 1. So I'm given u, okay, R uniform in 0 and 1. So let's say I have, I don't know, 1,000 samples, right? And using that, I want to generate my x. So x would be, indeed, I should define my lambda to be 2, right? So using this equation right here, I'm going to say it is minus 1 over lambda times log 1 minus u. So let's do a histogram of x. Looks like an exponential. Let's set the probability to true because I'm going to compare it with the density of the exponential. Okay, and now on the same plot, I'm going to define an x-axis, right? So sequence 0 till, let's say, down to 4 with steps of 01. And my y would be, I want the density of the exponential evaluated at x-axis with a rate of lambda, right? And there you have it. So let's color, let's put a purple, and let's color the true density as lime green, right? Give it a better line width to 4 maybe. Let us also increase my y limit because I don't like it. So between 0 and 3 maybe. No, that's too much. 0 and 2, yep. 0 and 2 looks good. Okay, line width is 2. Okay, looks good to me. One last thing is the breaks. So put in 30 breaks, and there you have it. We have a really good approximation. See that the true PDF and the histogram of the method using the inverse of the CDF are compatible, if you will. So let's do it again and again and again. That looks good. So that's all we have for this one. We did a lot of stuff in this lecture. I'll see you in the next one.